So you're able to see my screen, I suppose.
Yes, sir.
Yes, sir.
Yeah, so I will share the lecture notes today, and I have shared the solutions. I hope you have received the email of the quiz 2, and I will share the lecture notes today. Okay.
Okay, sir.
Yeah. Are there any questions on yesterday's lecture? So we have looked at this problem, and if you using the value of SUT to be 600 MPa, we have constructed an estimated experiment diagram. So SM is 0.9 SUT, that is about 540, right? And this is the line that we are interested in. And this is 0.5 SUT, that is 300. And now if you look at this diagram, if my applied stress amplitude is 100 MPa, then that is below this endurance limit, and hence we say that for this we will have infinite life. And if applied stress amplitude is 400 MPa, which is above the endurance limit, then you will have a point at which the failure happens. Then corresponding to that, you found it to be 3 into 10 power 4 cycles. So that means at this stress amplitude of 400 MPa, the component can last for 400 cycles. Okay. So this value of SM that we have taken, if the applied repeated loading can be applied through bending or axial loading. So we know axial loading is more severe, and hence the value of SM for axial loading will be 0.75 SUT. If it is bending, it will be 0.9 SUT. Okay. If at all you know the loading scenario, then you have to change the value of SM when you are setting up the estimated SM diagram. All right. So this is how the fatigue failure data usually is represented, SA or stress amplitude sigma A versus number of cycles to failure. And you see that for a steel, sigma U being 820 MPa, the endurance limit is found to be 410 or 414 MPa approximately, and which is 0.5 times SU sigma UT, and up to 820 into 0.9 is about 750 MPa. That is where your 10 power 3 cycles, you will have about 10 power 3 or 10 power 4 cycles, you will have your SM value, right? This is for steel, you can clearly see an endurance limit. Whereas for aluminum, you don't see. This is experimental data. You don't see any endurance limit. It continues to decrease. Even beyond 10 power 6 cycles, the fatigue strength continues to decrease. Whereas beyond 10 power 6 cycles, it is sort of constant for steel. Right? That is what we discussed in the yesterday's class. Was there a question? Someone was asking a question? No. Okay. So we have discussed that SN curve can be represented by S is equal to AN power B. The test data can be, so whatever test data that you have, you can use S is equal to AN power B to fit this test data. Okay. And for different materials, this test data has been computed experimentally, and you can see SAE steels, SAE 1015 steel, whose yield strength is 228 MPa, ultimate strength is 415 MPa. For that particular guy, A is 927 MPa, B is minus 0.138. So this data is obtained after doing several experiments for different kinds of materials. So we can use these values A and B, because there are two ways that you can represent the data. You can write sigma A or S is equal to AN power B or sigma F dash to NF power B, depending upon how you are choosing. You can. This is one model. This is a similar model where A is equal to 2. Here, whatever A is there, that will be 2 power B times sigma F dash. NF power B will be N power. It is just a rewriting of the equation. So we mostly use AN power B. So then A value and B value in the consistent units. Okay. Any questions here? No. So we have seen typical fatigue failure surfaces. If you look at it, this is where the fatigue crack gets initiated, and you can see the way the beach line marks are there, and suddenly you have a sudden fracture. Up to here, you have beach line marks. That means there is a gradual increase in the crack length. And when this crack length has gone to this level, then the crack became critical crack and there is a brittle fracture suddenly there. That is sort of, this is how your fatigue crack looks like. And similarly, you can see the beach line marks here. And basically, this is for a fatigue fracture surface. So this is the fracture surface due to a fatigue load of 18 Mn steel. This is the code of the steel that we are using. And here the fracture surface due to a fatigue for an aircraft propeller. When the aircraft propeller is failed due to fatigue, then the fracture surface has been investigated and it looks something like that. And for polymers, the fatigue stress life curves looks very different because they don't behave like metals and they do not show any endurance limit and so on. So you can actually use this data in order to find out A and B if required. Now, so the fatigue test data that we have done here, this is what we call a test data obtained by doing the rotating beam bending test. What do we mean by that? When I say I have done rotating beam bending test in order to obtain the fatigue data, what is the meaning?
We are
Like a
applying,
shaft, right? You are
Sorry?
applying a
Yeah, Pranab,
like
go
a
ahead.
fluid. You're
We are
going to
applying-
rotate the specimen actually. And
Yeah, so that means we are creating a scenario of fully reversed loading. Okay. So, but in reality, the components are subjected to some mean stress. That is one thing. And the rotating beam bending test is usually done at room temperature. But in reality, the components may be working at a different temperature. And this rotating beam bending test is done on a specimen of certain size. But in reality, the specimens will be of different sizes. So that means there are some variations to actual service conditions compared to the specimen geometry that is used, or specimen condition, test conditions and specimen geometry that is used for producing this data. But we only have this data. Now the question is, can I use this data irrespective of the test condition? It turns out that you cannot. The reason being, if you have a larger specimen, that means there are more number of cracks. That means the probability for failure is going to increase. So you need to somehow account for that. That means you need to do some correction to the actual service conditions compared to the this data, because the fatigue data is available for this fully reversed loading. And when you say A and B, this is obtained by assuming the loading conditions are according to some standards. But in reality, the material may not be the service conditions may not be exactly the way that they are in the experiment. Is that clear?
Sir, but for static loading, but do we depend on the experimental data, right?
Exactly. But static loading, the point is the difference between fatigue and static loading is that in static loading also the temperature is room temperature. If the temperature is different, then the stress strain curve will be different, isn't it? The yield strength of the material changes. Then we have to produce the stress strain curve at a different temperatures, isn't it?
Yeah.
In the case of static loading, we are only looking at the plastic deformation followed by fracture, but there is no repetition of the cycles. And even in the static tensile loading, we are interested in looking at the yield strength of the material, which does not change significantly because there are no other effects that we will see in the case of fatigue. Okay, we will see why it will not be possible to use the same conditions. Okay.
Yeah. Okay.
So we are now going to talk about corrections to fatigue strength or endurance limit. So the fatigue strength or endurance limit for materials is obtained by standard tests like rotating beam bending test. However, there will be physical differences between the test specimen and the actual machine part. So the SF dash or SE dash, which we call uncorrected endurance strength. That is why there is a dash here. SE dash is an uncorrected endurance strength obtained from experiments. You need to correct it for it. Now let us look at it. SE dash obtained from experiments is based on rotating beam bending test. But if you are applying axial loading, then the entire surface is subjected to same kind of load, and hence the probability of failure in an axial load scenario is much higher. This we have discussed yesterday. And hence, depending on the type of load, you need to account for that variation. Do you agree or not?
Yes, sir.
Yes, sir.
Yeah. Similarly, environmental factors. Suppose if you are working in at a different temperature range than what was done in the experiment, then you need to account for that. And because fatigue involves a lot of data, the fatigue data is known to have large spread, right? Because it's not very deterministic, unlike static loading. Unlike a regular tensile test where the data is highly deterministic, the spread is not very high. Whereas in fatigue, the spread is very high. Why was the spread very high?
Defects.
Because the defect structure could be very different in each specimen to specimen. And that leads to different types of cracks, right? So that means you need to have something called a reliability factor. What is the reliability level that you are expecting? If you want a high reliability, then you need to account for that. And specimen size effect, because if we have a small size specimen and large size specimen, it is not the number of defects per unit area that matters. It is the defect, that the number of defects themselves will matter, unlike in static test. So that means if your specimen size is larger than your specimen size used for obtaining SE dash, you need to account for that. And because here we are talking about crack propagation, if the surface is not clean, then you can actually have crack initiation from the surface. On a rough surface, the probability of crack initiation is much higher compared to a smooth surface. And hence you need to account for surface finish. If the surface finish here is some value, and in reality, the actual component is having a different surface finish, the properties is going to be different. Okay? So one needs to account for all these. So if you have an uncorrected endurance strength that is obtained from experiments of rotating beam bending test, the actual endurance strength that you will have on the component is multiplied by all these factors. Note that all these factors are less than 1. So the endurance strength of the material will be less than, corrected endurance strength will be less than the uncorrected endurance strength. So now let us look at each factor. Suppose if you are having load factor, if your applied load is bending load, then all this we are discussing with mean stress 0. That means fully reversed loading, mean stress is 0. Bending, there is no correction required. But if it is an axial load, you need to do the correction of 0.7 on the endurance strength. Is that clear? So if the load is axial, so instead of 0.5 SUT, SE dash is 0.5 SUT normally, but because it is axial load, 0.5 times 0.7 SUT. So that means 0.35 SUT will be your SE, corrected endurance strength. Is that clear?
Yes,
Clear,
sir.
sir.
Suppose if you have pure torsion, what we will do? Because this is only done for the axial load, but pure torsion will have only shear stress. What we will do then is, we will calculate the effective stress or von Mises stress from the pure torsion. And then you will use that stress for the calculation of your loads. And that will be used as a bending stress with C load equal to 1. That is the difference. Now size factor. The specimen size in rotating beam test, standard specimen size is 8 mm diameter, normally. So if the part size is larger than this, then a strength reduction factor should be used. Why? Because larger part size means more defects will be there. Because larger parts fail due to, at lower stress, due to high probability of flaw being present in large stress region. So for axial loading case, C size is equal to 1. For axial loading case, you need not account for size factor. Why? Because in the case of axial loading, failure in axial loading is independent of the cross-section area. Because everywhere you will have same load. Whereas in the rotating beam bending test, if you have a larger part size, that means there is more area that is subjected to higher axial stress. Whereas in the axial loading scenario, everything is same. So you should not apply C size for an axial loaded specimen. Is that clear?
Yes, sir.
Yes, sir.
One small question, sir. Like here, if I ensure that my part for a rotating beam is made of high precision and no flaws and all, then I can argue that I get rid of this factor, right?
No, it is not about the flaw size. This is about the specimen size. You are doing 8 mm diameter is the rotating beam bending
Ah, yeah,
data.
yeah.
If your actual part is
Okay.
greater than 8 mm diameter, if you have a circular
Because the
shaft,
argumentation is
hmm?
the argumentation is that we are putting this factor because we are trying to say that okay, you have a bigger part and the probability of having a defect in it is higher. So if I ensure that in my manufacturing, the part what I make is having a, let's say, flaws are very low or defects are low, then can I get rid of this factor C size actually?
No,
That was the question.
because you would have got, see, what are you doing in the, for example, if you are using SAE 1015 steel, right?
Yeah.
1015 steel, the manufacturing process is fixed. Right? So for that, if you are doing your manufacturing process separately, then for that manufacturing process, for that particular specimen, you cut an 8 mm diameter specimen and do the rotating beam bending test, and from there you measure the SC dash. Okay.
Okay, got it.
And now if you are using the same material for your product, and if that product has larger diameter, again you need to apply the size factor.
Got it. Okay.
Yeah. So if the diameter is less than 8 mm, you need not worry about the size factor, because D8 mm, less than 8 mm is not going to be worse than 8 mm. So that's why there is no need for size factor is 1. That means it is not accounted for. But if the diameter is between 8 mm and 250 mm, this is the formula that one needs to use. You don't remember this formula, this will be given in the exam, or the people have come up with. If it is greater than 250, size factor is fixed at 0.6. It will not further reduce. So this equation is valid only for steel. For non-ferrous metals, these equations are not precise. So you need to look at the charts and get the C size factor. So here we have talked about circular cross section, but in reality, you may have non-circular cross sections, right? So you please read Norton's machine design textbook on how to account for non-circular cross section. Here I will talk about, quickly describe. Suppose if you have a non-circular cross section and non-rotating round bars, if the bar is not rotating, okay, and you are applying bending cyclically. Now, let us say if it is a non-circular cross section, all that you need to do is the following. If you take this circle, the maximum stress will be in the outer layer. Do you agree or not? And
Yes.
the stress will vary linearly from the center of the shaft to the outer layer. Like that. It vary linearly. So it is 100%. And if you are at 0.95 times R from the center here, if you go 0.95 times R, right? No, this is R, and so this is outside is D, and inner circle diameter is 95.95 times D. If you draw the inner circle, this is the region, that area between these two circles is the region that is experiencing greater than 95% of the maximum stress. Do you agree with that?
Yes.
Yeah. So now all that you need to do, you calculate A95 for this shaft. A95 is if the outer diameter is D, inner diameter is 0.95 times D. So the area 95, that means the area that is experiencing greater than 95% of the stress is, for a circular shaft, is 0.0766 D square. Then I compute the D equivalent is equal to square root of A95 by 0.0766. Suppose if you have a non-circular cross section, all that you need to do is in that non-circular cross section, what is the area that is experiencing greater than 95% of the maximum stress. Okay, and that area you substitute here, then you get an equivalent D. And if this D equivalent is greater than 8 mm, then you will use this formula. Is that clear?
Yes, sir.
Yeah. So now suppose if you have a rectangular cross section, so you would see that if it is not rotating, only 95% means 0.05 BH, because up to from here to here, the highest stress will be here, and 0.05 BH, B times H will be the area that is experiencing greater than 95% stress. So that is, you plug in A95 as 0.05 BH by 0.076, and that will give you equivalent diameter. Okay. And if it is non-rotating, if it is rotating shaft, this is the one. If it is non-rotating, only a greater than 95% means it will only happen here, and that will be 0.01046. You can do that computation, and then from there you will calculate D equivalent is 0.370. If you have a section like that, right? If it is an I section, then A95 along this 1-1 axis, A95, because when the bending is about 1-1 axis, bending is about 2-2 axis, you calculate these values, and these are available again in the literature, and you calculate A95 and plug it in this equation, and then you will calculate, you will obtain D equivalent for a non-circular or non-rotating section, and you plug that in into then from there you calculate D equivalent, and then compare the D equivalent value with 8 mm. If it is between 8 and 250, you will apply this formula. Okay. So that's about size effect. Now coming to the surface effect, you know that rough surfaces reduce the fatigue strength, isn't it? So in a material, rough surfaces reduce fatigue strength because they are the what you call triggers of cracks, surface cracks. So normally for cast iron, you don't have to give any surface factor, as in cast iron, because the internal pores dominate compared to the surface pores. And hence for cast iron, you don't need to give any surface factor, because the effect is mostly, the failure mostly happens due to internal pore structure. However, for steels, it is not like that. So if you are electroplating the surface with metals, drastically reduces the fatigue strength. So now you look at what are the, how do you give, say, various surface. Suppose if the surface, this again, you give this formula C surface equal to A SUT power B. This A and B are different from our S is equal to A n power B. These A, B are different. So if the surface is ground surface, then S will be one, these values. If it is machined or cold rolled, hot rolled or as forged, these values will be different. And as forged will be very rough compared to hot rolled and so on. That is why these factors will increase the value of surface, reduce the value of surface. And similarly, temperature, if the operating temperature is less than or equal to 450 degrees Celsius, there is no need for temperature compensation or correction. But if the temperature is between 450 to 500, 550, then the C temp is this, because this is mainly for steels, and steels usually are not used beyond 550 degrees Celsius, and hence this temperature correction is only given up to 550 degrees Celsius. Now, the rotating beam bending test, we consider the reliability of the data because there is large spread, only 50%. But if your actual design requires higher reliability, then your reliability factor reduces. If you want 99.999% reliability, then you get 0.659 as your reliability factor. These are all available in the literature because these numbers have been arrived at after doing several experiments. So now let us talk about the estimated SN diagram. We have already discussed. We know that HCF regime is between 10 power 3 cycles to 10 power 6 cycles. Corresponding to 10 power 3 cycles, you have SM. If it is bending load, you will say 0.9 times SUT. If it is an axial load, you have to use the SM as 0.75 times SUT. Okay. Usually the correction factors should not be applied to SM. SM does not have correction factors. But now you have to apply correction factors to SE dash. What is SC dash? SC dash is equal to 0.5 times SUT. So if the material exhibits a knee, then corrected SE is plotted at 10 power 6 cycles. If there is no knee, corrected SF is plotted as SC 5 into 10 power 8 cycles. You know, the line from SM to SE is represented by S is equal to N power B. This is S of N. S is a function of number of cycles. So, all this we have seen yesterday. I don't want to get there. Now we are trying to solve the same problem that we have done yesterday. Okay, let me get back. Please note down the conditions. I will open my iPad. In the meantime, please note down the question. It is exactly the same question, but now you have corrections. Have you written down? You're able to see my screen, I suppose.
Yes, sir.
So here we need to create an estimated SN diagram. We know sigma UT or SUT. I might use sigma and S interchangeably. Please bear with me. 600 MPa. It is a assuming that it is bending, right? SM is equal to 0.9 times SUT, that is equal to 540 MPa that we have done yesterday, right? So corresponding to 10 power 3 cycles, we have 540 MPa. Now we have SE dash uncorrected endurance strength is 0.5 times SUT, that is equal to 300 MPa. Now you need to do the corrected endurance strength, that is C size, C load, C temp, C surf, C reliability, and what else? If I forget anything, I will get there. Right now, let us look at the problem. The bar is 150 mm. That means the diameter is greater than 8 mm. Isn't it?
Yes, sir.
So, because it is greater than 8 mm, unfortunately, it is what do you call circular. I didn't have to do anything much. So, this is the what do you call the condition for C size. So, what should I write? Now I can calculate C size is equal to 1.189 into 150 mm, right? D is 150. 150, you should not convert this into meters because this is written in mm. So directly it should go. This is an empirical relation, so they may not have any meaning with respect to units. So what is C size?
.73.
C size is?
0.73.
Is it 0.73?
Yes, sir. 0.731.
Okay. Okay. One problem that we had. Yeah, 0.73, right? Now that is assuming it is a circular one. But if you carefully observe, this is a square one. It is not circular. So I have to calculate A95, isn't it? A95 will be 0.05 BH, that means B square. That means 0.05 into 150 square, isn't it? So I cannot use 150. 150 is the square size, but I have to use equivalent diameter, isn't it? So I have to say D equivalent is equal to square root of A95 by 0.07 66. So first I need to calculate A95. What is A95? Because it's a
0.05 into 150 square.
yeah. No, A95, what is it? 0.05 into 150 square.
1125.
1125.
5% of
So that is 1125 divided by 0.0766 under root. That is giving me 121.2. Now in this I need to plug in 121.2, not 150. So a small oversight would have caused a lot of trouble, isn't it? Is this process clear? How we are calculating C size?
Sir, if it is in case of bending, the area would change, right?
It is a bending load.
Point 746.
Point
746.
746. So I have calculated C size. We also forgot about C load. What is C load? Because it is not given. So if you look at this fellow, create an estimation diagram for steel bar and define its equation. How many cycles of life can be expected? Loading is fully reversed bending. So C load will be 1. Isn't it? And then it's a hot rolled finish. So if it is hot rolled finish, so hot rolled finish, C circ is equal to A times SUT power B. And it is hot rolled, right? So that means 56.7 times SUT is how much? 600 MPa in MPa whole to the power minus 0.718. That is B. Right? What is that value? That is my C circ. Is that clear? Because it's a hot rolled material. Here it is given it is hot rolled finish. So you have to take appropriate surface finish factor.
Point 574.
Point
574.
0.574. Okay. And then, is there any other answer? So here is operating at what temperature? 500 degrees Celsius. So that is greater than 450 degrees Celsius, isn't it? So now I need to calculate C temp. So the C temp is equal to 1 minus 0.0058 into 500 minus 450. What is C temp then?
Point 7.
Good. Any other thing that we forgot? Reliability factor, 99.9. Right. So I need to get that reliability table. So C reliability at 99.9%, right? Therefore, that is equal to 0.753, right? Now I can write the corrected endurance.
Sir, one more thing. Infinite life required was written. Do we need
Yeah,
to
that means
anything
10
for
power
that?
6 cycles. Infinite life means you are talking about 10 power 6 cycles, right?
Okay, yes, sir.
Yeah. Corrected endurance strength SE is equal to C load L, C size SZ, C temp, C reliability, C S surface times SE dash. What is C load 1? C size 0.746. C temp 0.75, sorry. C temp is 0.71. C size, C reliability is 0.753. And C surf is 0.574. Anything else that is remaining? Nothing. Into SC dash is 300. Uncorrected endurance strength. So what is this value?
68.7.
Sorry?
68.7.
68.7 MPa. Right? So earlier, if you look at our graph, so maybe I will get that graph here. Right? This is the uncorrected one. In the uncorrected, this is 300, right? SE dash. This is sigma A. Then we have seen that to be safe. But now let us draw the corrected one. This is the corrected estimated diagram. Then you will see that your SE is here, corrected one. It is around 68.7. Now, in the case of uncorrected, if you are applying 100 MPa, you found it to be safe, isn't it? But with after applying corrections, because the situation has changed, after applying the correction, 100 MPa would become, it's not going to give you infinite life. Any stress below 68.7 MPa will give you infinite life. Otherwise, it will have finite life. So here, what is the failure point at 100 MPa? What is the failure point at 400 MPa? Because you can find out, right? So in order to do that, first of all, you need to find out the line. How will you find out? So you have SM is equal to 540 at 10 power 3 cycles, and SE is equal to 68.7 at 10 power 6 cycles. Right? So now you know that SC is equal to AN power B. Let us say this is 0.1 and this is 0.2. So S1 by S2 is equal to N1 by N2 whole to the power B. That implies B is equal to log S1 by S2 divided by log N1 by N2 that we have seen yesterday. that is equal to log 540 by 68.7 divided by log 10 cube by 10 power 6. That is your B. So that results in the B value point minus 0.29, something like that. Can you check? What is this value?
Minus 0.298.
Minus 0.298. Okay. Now A is equal to S by S1 by N1 power B. S1 is 540 divided by 10 cube whole to the power minus 0.298. What is that A? You understood, no? How am I getting A? I am using one of the points to plug in. What's the value?
4.24 and 10 power 3.
So 4.24 into 10
10
power
power
3, that means 4240. Therefore, your equation is equal to S is equal to 4240 n to the power minus 0.298. That is your SN curve, isn't it? Now, at 100 MPa, what is the life? So n equal to log 100. So how do you calculate? Not log, sorry. N is equal to 100 divided by 4240 whole to the power minus 1 by 0.298. N at 100 MPa. What is that? Number of cycles for failure, NF at 100 MPa. Similarly, number of cycles to failure at 400 MPa. NF at 100 MPa. And this is 400 MPa, that means 400 by 4240 whole to the power minus 1 by 0.298.
.9 into 10 power 5. Sir. That's
2.9 into
10 power 5.
For 400 cycles.
Second one 2.77 10 power 3.
Okay. Is this clear? Are there any questions in this problem? All that we have done is in the previous problem, when you add correction factors, of course, the life will change. That's what we have observed.
Sir, one clarification here.
Mm.
When we are modifying the endurance limit, actually, then we are only concentrating on a high cycle fatigue, right?
We are
not
only
bothered
talking about high cycle fatigue in this at this point of time. We are not talking about low cycle fatigue at all.
Okay.
Because we are only talking about this line. That is only greater than 10 power 3 cycles. That is HCF regime, right? This is
Yes,
your LCF
yes.
regime. Okay.
Similar approach, you get it for LCF also? Or?
LCF, we will do it in a different way. We will talk about it. Yeah, there are
Okay.
different models for LCF that we will do it later. Okay. Then you will not use stress life approach, but you will use something called strain life approach.
Okay. Yeah.
Any other questions?
Professor, on the failure point, how to figure out, sir?
Can you say again? Because what do you mean by how to figure out?
In the graph, you mentioned failure point, right?
Yeah. So all that I'm saying is, you have got this figure, right?
Yeah.
You have got the SN diagram. This line is known. This is what you have constructed now.
Yes.
By knowing this point and this point on a log plot, it's a straight line.
Yes.
But in the normal line, the equation is, this fellow is your equation. Correct?
Yes. Yes, sir.
Now, all that you want to know, what is my life at 100 MPa? So on the y-axis, you look at 100 MPa. Corresponding to that, wherever this line,
Okay.
excuse me,
Yeah. Understood, sir. Yeah.
wherever that line intersects the failure line, that will be my number of cycles to failure. At 400 MPa, the number of cycles to failure. Excuse me, I think it's an urgent call. Maybe I have. I'm sorry, for the disturbance here. I had to take that call. Okay, so any other questions here? If there are no further questions, then we will move on. Yeah, so let me change the screen. Yeah. So now let us look at another problem. You're able to see the screen, right?
Yes, sir.
Yeah. So sometimes right now what we have done is, we, by knowing the SUT, that means ultimate tensile strength, we have constructed an estimated SN diagram. Correct? We have not really taken the values of failure from some test data, but by knowing SUT, because it is still more or less, we understand it is 0.5 SUT and applied the correction factors and so on. Correct? Now, instead of that, if you have a test data, so for example, in this slide, we are having test data wherein when you apply a stress amplitude of 948 MPa, the number of cycles to failure is 222. In the figure that we have shown earlier, so they are giving these points on this graph. Okay. So if you have a 948 MPa, you are having a 222 cycles of failure, 834, 992, and so on. And now, if this trend represents a straight line on a log-log plot, then what will be the values of A and B? Okay. So this is the test data for stress amplitude and corresponding cycles to failure. The tests were done on unnotched axially loaded specimen and with zero mean stress. That is the scenario. Okay. So now how do we go about it? Can you come up with some ideas as to how to go about such a scenario? Can you think of?
In Excel, I'll put this data and create a curve and
Yes.
a to the power a into n.
So all of you are in front of a computer, right? All of you are in front of a computer because you are joining via computer. Please use this data and fit a curve in Excel, and that curve should be S is equal to n power b, and find out A and B. Please do that. I am also doing while you are doing that. How many of you know how to fit a curve in Excel? How many of you don't know? Please let me.
We are trying, sir, here.
Yeah, please do it. I think a large fraction of you must know Excel. You must all be much better than Excel than I am. So
I am getting 7e33 x to the power minus 10.58.
anyone else gets the same thing? What are you fitting? What kind of equation that you are fitting? You are adding
made
a
a
trend,
power
law, trend line for the power law.
Yes.
So your x-axis is what? What is your x-axis?
Cycles.
N or S?
Number of cycles.
Did you keep x-axis as number of cycles?
Let me check. I think I meant.
this is what I got. Because this is N is your x-axis, S is your y-axis. You're able to see my screen? And I have plotted the data and I have fitted a power law, and the power law equation is 1584.2 into x times s to the power of minus 0.994. Here x is N, y is S, because first one is N. So you can see x is N, y is S. You must have done the opposite.
Yes, yes, I made a mistake there.
Right? Okay. Now this is your so 1584.2. So I can say now in this, if you don't, normally the best way to do it is what we have done. We have to fit a curve. But sometimes you don't have the possibility to do curve fitting, then you can take any 2 points and try to fit a straight line, any 2 points. Or using those 2 points on log plot, you try to fit a straight line. I did with 948 and 524. Then I got 1565 and minus 0.0928. Not very bad, right? Even with 2 points. Right approach is to fit a linear line, which actually we did, and that is 1584.2 into times n power minus 0.094. That is the better result. Any questions there?
If we take next points, actually we may get
It may be different. It may be different. Yeah, I agree with you. So the best thing is to do fitting a straight linear least square fit for the data that you have done. So then that is how the stress life equation looks like if you would plot. Now let us discuss safety factors. Okay, so 1 minute for some reason. Yeah. For some reason, this mouse is not working. So you're able to see the screen, right? Yeah.
Yes, sir. Yes, sir. Yes.
Yeah. So now we will define safety factors on SN curve. So let us say this is your SN curve, right? Suppose if you are operating at this particular stress amplitude and you have designed your component, let us say, saying that I have designed my component such that it works at a stress amplitude of sigma A hat for n hat cycles. At this particular stress amplitude, you have designed the component for n hat cycles. That is your design point. Now, if you have to define factor of safety, there are 2 factors of safety that we have to define. One is called factor of safety in life, and that is what is Xn. Another is called factor of safety in stress, that is Xs. So suppose how do I define factor of safety in life? Suppose if I have to operate at sigma A hat, I have the design number of cycles is n hat, but in reality, the component could be used up to nf2. Can you see that? Because that particular stress amplitude, my actual failure happens here. Needs any number of cycles. So factor of safety in life now will be nf2 by n hat. How do I define factor of safety in stress? If I were to get these many number of cycles of failure, then I am only telling that I can operate at sigma A hat. But in reality, the material can take up a stress amplitude of sigma A1. So then my factor of safety in stress will be sigma A1 by sigma A hat. So that is how you define factor of safety in life and factor of safety in stress. Is that clear? The definition. Okay, if that is clear, yeah. So now usually the values of factor of safety in stress will be very similar to what we have learned in static failure theories. Factor of safety values will be between 1.5 and 3. But factor of safety in life will be large numbers, usually between 5 and 20. Sometimes it can be 100, 200 like that. So don't get surprised if you see a factor of safety of 200. That is not in stress, but that is in life. That is normal. Okay. Now, for the fatigue stress life data shown in the table that I have shown you before in the previous slide, for which we have computed the values of A and B. What was the values that we have computed? We have computed to be with 2 points. We have taken this, but when we have fitted the data, what was the value? 1584 and
minus 0.094.
minus 0.094, right? So you replace that or use this, it does not matter, but that is what you need to do. Now, what I wanted for that particular data, A and B are given. A stress amplitude of 200 MPa will be applied. So this is the service condition. Will be applied in a service for 2000 cycles. That is the status that is given. Now you need to estimate the factor of safety in stress and life. How do you go about doing that? Can you please try that? So now this is the data for which we got S is equal to 1540 times n power minus point. What is it? Minus point?
0.094.
0.094.
That is my SN curve for this fellow. So this is 10 power 3 cycles. This is 10 power 6 cycles, let us say, right? In 10 power 3 cycles, what will be my S? Can you plug in 10 power 3 and tell me what is this value? And at 10 power 6, what is my S? If it is a
Uh, 804.5
where 804.5?
per 1000, 10 power 3.
804.5 and here
420.26. 420.
420.3.
That is what we are talking about, right? That is the line that we have. The equation of that line is this. That is 1540 n to the power minus 0.094, right? That is how the line is going to be. Now he is asked us to find out what is at 500. So at 500, sorry, he did not say at ask. He said, let us say this is 2 into 10 cube, that is 2000 cycles. This is 500. So this is the design point. That is 2000 cycles and 500 MPa. Right? If that is the design point, what is the factor of safety in life? What is the factor of safety in life is n, factor of safety in stress. That is what he's asking us. Right? So now, if you have to factor of safety in life, I need to find out what is NF,
Total number of cycles. Yeah.
number of cycles for failure at that particular stress. So that means I need to find out NF at 500. That is equal to S is, so this is, I need to find out NF at 500 means 500
500.
by 1540 into minus 1 by 0.094 is equal to NF at 500. Do you agree?
Sir, one question actually, if I plug in 2 into 10 power 3 in the equation, I'm getting 753 as a stress actually.
No. That is this value. 2 into 10 power 3 will tell you this at 2 into 10 power 3. What is the value of that? Failure.
Okay, got this. Okay.
That is, I am calling it as sigma F. Isn't it?
Yes, sir.
This equation represents points on that line only. But
Okay.
your component is designed for that. Now I wanted to know if you are operating at that particular 500 MPa, how many number of cycles that the component can last?
157524.
Sorry?
1.57 10 per power 5.
1.57 into 10 power 5.
Yes.
Now, so factor of safety in life is equal to NF at 500 divided by NF hat, number of cycles of life that it is designed for. N tilde, not NF, N tilde. Is not number of cycles for it is designed for. Correct? 1.57 into 10 power 5 divided by 2000. What is the factor of safety in life?
78.76.
Sorry?
78.76.
Now, factor of safety in stress will be sigma F divided by sigma tilde. Sigma F at 2000 cycles. Correct? Sigma F at 2000 cycles divided by applied stress. So how do I find out sigma F 2000 cycles? That is 1540 into 2000 to the power minus 0.094. Correct? If you
Yes.
plug in that, and that someone told me that 700, what is the value?
753.7.
753.7. So this is 753.7, but it is actually, the component is only subjected to 500 MPa. So that is the factor of safety, right? This is the failure stress. This is the applied stress amplitude. In that sense, it is a stress amplitude that we are talking about.
1.5, sir, factor of safety.
All right. So that is how you can compute factors of safety. Is that clear?
Clear.
Any
sir.
questions here?
Okay, the no.
Sorry?
It's clear, sir. It's clear.
It's clear, right? Okay. All right. Then I think we'll stop here. So we have now looked at how to draw an estimated SN diagram, and then given a data, how to fit a power law and get A and B. And we also know how to incorporate correction factors And we also know how to compute factors of safety in life and stress. All this we have done under the condition that it is fully reversed loading. That means the mean stress is 0. Correct? So in the next week, what we will look at is what happens if the mean stress is non-zero. That means the loading is either repeated loading or fluctuated loading. How do we go about solving that problem? That is something that we will look at in the next class. Is that clear? Okay.
Yes, sir. Yes, sir.
Yes.
Yes, sir.
Yes, sir.
Okay. All right then. Thank you very much. We'll meet next week. Thank you.
Sir, hello.
Yes.
Sir, next Friday you ask for the class now, sir. We can have it after 5:30, sir. Up to
Okay.
5 o'clock. Up to 5 o'clock only we have the project review. After that, we are free.
Absolutely fine. Thank you. So we will arrange a class next Friday. Absolutely. Yeah.
5:30, sir.
5:30. Not this Friday, but next Friday. Okay.
Yes, sir. Yes, sir. Okay.
Thank you.
Sir, next Friday we have some project, actually not project, but we have to present for our additive manufacturing some of the presentation. The timing
What?
has yet not decided actually.
Additive manufacturing course. Who is teaching?
Professor Jnanamurthy.
Jnanamurthy. Okay. So, but can you inform him that we have a class at 5:30?
Sure, sir. Sure.
Yeah, you inform him. If he says that it is not possible, then we will reschedule. Otherwise, we will stick to 5:30. Okay.
Okay.
Yeah. You please inform Femina or Subbalakshmi, whoever is your in charge. So then accordingly we will plan.
Sure, sir. Sure.
Yeah.
Okay.
Thank you.
Thank you.
Thank you.
Thank you. Thank you, sir.
Thank you, sir.
Sir, please upload the notes today.
I will do it.
Sure. Thank you, sir.
Thank you, sir.
Thank you, sir.